That's what I get for letting you guys play with the recording functions. Okay. Try not to turn off the recording again, please. So when we're talking about file systems, as usual, we'll talk about some of the assets that you need to have a file system, and we'll look at how they might be presented in different operating systems. And of course, as ever, those different assets might be shown differently, they might have taken a different approach, or they might have chosen to do something else entirely. And of course, that's one of the things that we'll cover, the different approaches we might have and the reasons that we have them. So we'll look at all sorts of aspects around the file system and try and come to a consensus about what a file system should look like. So for example, one of the things we have to decide first of all is what we're going to store. What do we define as a file? Is it just text? Well, no, because text isn't just text. Text is a set of numbers that we think of as text. So it has to be data. So data is a whole bunch of numbers. So ASCII 32 is a space. Of course, ASCII 32 is just 1 0 0 0 0 0 in binary. So in essence, what we end up is all data is binary, which means that we can have all sorts of data stored in binary files, including the case where that file is a program itself. So it's up to the person who creates it what that file is. And they will often attach information to it. Now, some of the information they will attach, so you create a file and you give it a name, but some of the information is attached by the operating system, and different operating systems will attach different types of information. Some of them are pretty universally across operating system. So I can't think of a single operating system that doesn't store the size of the file, for example. Some operating systems store when the file was created. Some operating systems store when the file was last accessed. Some operating systems store when the file was last modified. And some operating systems store a combination of all of those. So it does just depend. But the sorts of things that you can see on the slide are a fair representation of the sorts of things that a generic operating system would store. And we can see that if we look at a specific one. So here is the file information box from a Mac. So you can see that someone has created a file. They've named it 11, but it also has a dot and then some letters after the name. Again, I apologize for anybody who's listened to me going, really, you're telling us what an extension is? Yes, I am, because not everybody will have thought about it in these terms. And don't forget, the default for something like an up-to-date Windows system is not to show extensions. Some people may not even be aware that extensions exist. They may instead look at something like File Explorer in Windows and just see what type of file it is, a Word document or whatever. In this particular case, there's a dot followed by a three-letter extension, TEX, which identifies this as a text file. If you're not aware of it, don't worry about it. It's a markup language. It allows you to mark up documents quite often before they're printed. It gives you the size of the file, and interestingly, it also tells you how big it is on the disk. Why is there a discrepancy between the file size and how much space it takes on the disk? think back to our previous lectures when we talked about allocating space on a disk. Why is there a difference between the actual file size and the space it takes on the disk? The answer, of course, is because we have on the disk, when we talked about file allocation, we talked about pages, when we talked about blocks. On the disk, when you set up a file, it takes a block, and if the file gets bigger, it takes another block, but that block may not be full. So that block of data on the disk may not be full, and that's the discrepancy there between the actual size of the file and the space that's been allocated on disk. We've also got a where, and we'll talk more about directory structures later, but that's a directory structure. You can see there the Mac operating system stores both when it was created and when it was modified. And don't forget that under the hood, the Mac operating system is a Unix operating system, so Unix does the same thing. But because it is a Mac operating system, it adds some other features, specifically a label, so you can assign colors to it. So it's a shame that this screenshot's in black and white. It's got some other info when it was last opened. The Mac also allows you to hide the extension if you want. And you won't need to have the extension because you can see right at the top it told you it was a text file anyway and gave you a nice wee icon for it. It's associated with a program, in this case TextMaker. And it also has permissions. Who can access this file? You can see that in the where, it's stored in users Greg. So it's a fair bet that this belongs to a user called Greg. And that suspicion is borne out when we look at who can access the file. Greg brackets me. So this is Greg's file, and Greg can read and write. But he's decided to make it available to everyone. So in the same way as I've given you your module information and your student information in OneNote notebooks, you can read that file, but you can't write to it, you can't alter it. So everyone in this class has read-only access to that file. In this case, staff have read-only access. But everyone else who's not either that person or in the staff group has no access. And that's completely analogous to your module materials. I have access to that file to read it and alter it. So I've got read and write. This class has read-only access, so you can view it, but no one else in the university has any access to it at all. So these are fairly standard options for any file. But of course, one of the things we have to do is get a file. And you can see there one of the things is when it was created, and that's one of the operations that we have to have for files, create files. And we can start to think about other things that we might want to do as well. We probably want to put something into the file, so we want to write it. We probably want to get something out of a file, so we want to read it. And again, if you've done any sort of programming, these things won't be a surprise to you. There's stuff in every programming language that says read a file or write a file. What there isn't in that programming language is anything that says read a file from a hard disk or an SSD or a USB or a OneDrive disk or a Dropbox or a Google Drive or an external CD or a net. Well, you get the idea. That's down to the operating system. That's one of the things that the operating system has to do. It has to present all of those devices and all of the files and directories on those devices as one homogeneous file system for the user. So you don't think about where the file is or the different mechanics involved in saving something to a hard disk than on a USB drive. You just say save file thread.txt, and the operating system takes care of that. It also takes care of the operations that we're going to have to do when we get to the file. So when we are reading a file, when we open a Word document, we don't bring it in all at once. It's probably too big to do that. We probably get it in 2K or 4K chunks. So we have to move through the file. Get the first 4K chunk, get the next 4K chunk, get the next 4K chunk. So that suggests that we can move through the file in some way. So we can seek and find bits in it. How we do that might depend on the type of file it is, and we'll talk more about that later. So there's a pile of functions there, and they're not exactly rocket science. We want to delete files, we want to do whatever. One of the things that we want to do when we have files and when we have them open is to try and figure out what restrictions that then places on us. You have your module materials. Ailey can open it, and Sumana can open it, Jennifer can open it, Harry can open it, and you can all open it at the same time. And that's not a problem because you're just reading it. So you can just read the file and have it displayed on your screen. But what if you're working on a group report on your OneDrive? What if two of you want to change that file at the same time? Who would win? Who gets to change it? And if you change it and don't save it, and then somebody else comes in and changes it again and does save it, are your changes lost? So when we have open files, we have to take some note of what's happening. If you're just reading them, it's fairly straightforward. We have a file open. We don't open it multiple times if multiple people are accessing it. We just open it once and we allow multiple people to access it. But that suggests that we keep a count of how many people are accessing it. And then when people close it, we close down that count until eventually we don't have the file open anymore. So when the count goes to 0, we close the file. We also need to keep track of where we are in the file. Which bit of it are we looking at? So as I say, we could all open this operating systems file. I could be looking at this page, and you could be looking at that page. So we're at different points in the file. So we need a file pointer to say where we are. And everybody who opens the file will need a different file pointer to figure out where they are. We also need to know where that file is on disk so that we can go and get more data if we need it. So if I decide to jump to a chapter that I've never had open before, it has to go back to the file, and you could actually see the pause there. It hadn't just been open, it wasn't in my cache, it took a wee bit to go back to the file, open it up and bring it in. So we have all of these different things that we're needing to keep track of for open files. Including something that we call locking. So this is the idea that we have multiple people who can access a file if it's a multi-user system. They might have rights to access it. But what happens in terms of altering it? Do we, for example, just say, okay, the first person to open it with who has the rights to change it, once they have opened it, that file is locked for writing apart from this one person. Everyone else can open it, so they can read it while it's going on, but they can't change it. So it will depend what kind of lock that you have. Is it a shared lock, so you can view it? Or is it an exclusive lock where you can write to it? Other operating systems extend that out. So for example, if you're running a huge Oracle database with tens of millions of records, so say you're working in a call center, and you have a client database, and everybody that's working in that call center has to go to the client database, open up the client database, phone them up, and then make a record of what's happened in that call. Now, you might have 100 people in that call center. You can't wait until someone else has closed down the file so that you can open it in write mode, then update, and then you close the file for somebody else. Then they update it, and then they close it, and somebody else gets in. It would just be impossible. So there's a middle ground. Some programs and some operating systems give access to a file on a record basis. So instead of just locking the file, they lock a specific record in that file. And in fact, if you run an Oracle database, you tend not to just run an Oracle database like you think of Access running on your machine. An Oracle database is in essence an operating system as well. So you would actually configure your system to do that. And lots of huge database solutions take that approach because it's so linked into what we have to do here in terms of multiple people accessing and altering data. So we can have record locks as well as exclusive file locks. So it starts to get a wee bit more complicated. If you're not aware of file extensions, there's some sample ones for you. But I would be quite upset if you'd got to second year and didn't know that these things existed. Okay, so let's think about different types of file. Because there are different types of file. You might get, for example, files that are purely text. So, for example, that's not a punch machine I want. In the early days of computing, what you might have had was a text file which stored data. And that text file was split up. So, for example, the first 10 characters you could define as the first name, the second 10 characters you could define as the second name, and so on. So you'd get something like this. No, not that. You get something like this. You get a COBOL programming sheet. Oh, wasn't expecting that to be Twitter. Well, what you would do is you would actually set up the data to appear in different columns. So if you read the data at column 40, you knew that was the postcode and was 8 characters long. And if you read the data at column 60, you knew that it was the phone number and was 10 characters long, and so on. You still get lots of files like that. Simple, line-based, fixed length data. A lot of the banking infrastructure runs on exactly these kinds of files. So you might get simple structures with lines and fixed lengths. You might get more complex stuff, like a Word document, or a Photoshop, a JPEG, or whatever it happens to be. In either case, of course, it ends up being a binary document. It's how you interpret it. And that's why some operating systems have chosen an extension, so that you can say, I want you to interpret this as. And of course, sometimes you might have competing programs. Since I installed Edge on my machine, Edge has insisted that it opens PDF files rather than Acrobat opening them, which is a bit irritating sometimes. So there's a thanks for following me, Anne Savannah. You're going to be disappointed in my Twitter feed, I must admit.
Well, not disappointed, I'm just surprised. What a pleasant surprise.
What, that I've got a Twitter feed?
No, that you are a counselor.
A man of many parts. So we have to decide how we interpret all this binary data. Is it a simple record structure fixed style? Is it a complex structure? And is that complex structure describing a Word document? Is it describing a JPEG or whatever? That is reflected in how we access the files. So we have something called a sequential access file, where we simply run through a file from beginning to end, reading the data. Virtual hands up on Teams, how many people remember cassette tapes? Every year I'm finding my cassette tape analogy isn't understood by lots of people. Yeah, I've got a few of you. A cassette tape is just one long tape where if you want to play something, you start at the beginning and go through. If you want to play the next song, you fast forward and hope for the best. We don't do that in computers. We have more than hopes for the best. We have them set up so that we know how far through we are. We can move through specific amounts, but it's the same idea. And you might be thinking, well, what do I care about cassette tapes and what do I care about computer tapes? And if you're not even sure what I'm talking about these things here. The sorts of things that you see in every self-respecting Bond villain's lair, or from any dystopian thriller from the 1960s. Big tapes like that, where data is stored, and you can almost see there, because the tape is going a wee bit at a time and then another wee bit, that's the computer reading each record. So you get a very visceral understanding of how the data is moving through, and that's physical tape there moving through the disk. And again, you might be thinking, well, why do I care? Well, you care because we still use them. This is from 2018. It's posted just last year. And this is called a tape library. Come on, play. Yeah, we'll pass on the music. Any decent sized data store, what you can see there, the whole bunch of tapes, and you have robots that go and get the tapes and put them into tape readers over here. And any decent sized backup operation will still use this technology. Why? Because it's really reliable and really cheap. So pennies per terabyte to do backups. And for people who need backups, so for example, if you're a bank and you need to store data for whatever the financial rules are, I always get confused if it's 7 or 25 years because there's different bits. In either case, you don't want your expensive hard disks used to store archive transactions. So stick them all in a tape and stick them all in a box in a safe somewhere. And then if you need the data, come back and get it. The last time I checked, that webcam was still running, by the way. So you can actually see data getting retrieved in real time. How many of you have heard of AWS? Virtual hands for those that have heard of AWS? Yep, some of you. So Amazon Web Services is, for those of you that don't know, is where Amazon makes its money. It doesn't make any money selling you books. It makes a loss on them. It makes money selling tech, selling storage, selling virtual machines. And one of the things it sells is something called frozen storage. Under the brand name S3 Glacier. Because Glacier sounds really good. So does secure, durable, and low cost, because they are really good. What Glacier means is, we'll take your data, we'll stick it on a tape, and we will put it in a cave. And I'm not kidding, it's literally a cave. One of the storage facilities is an old cave, one of them's an old US nuclear bunker. They put it in a cave, and then when you want it, you ask for it back, but you've got to give them 24 hours because somebody's literally got to walk into the cave, grab your tape, stick it in a machine, and retrieve the data. But that's okay because you can store data for 1 terabyte a month, which is insanely cheap.
Tony, I do not understand this bit that you just said. Do you mean that the data is stored on a tape and physically, I mean, the data is kept on a tape and physically stored in a bunker or in a cave? Is that what you mean?
Yes. That's exactly what I mean. It's copied from the hard disk onto a tape that looks something like that. And then that tape is taken out of the tape drive, put in a box, and put in a cave. So there you go, that's a Hewlett-Packard tape. So each tape will do 6.25 terabytes. It's for a 20 pack, it will cost you 500 quid. So 125 terabyte backup for 500 quid. Insanely cheap.
Yeah, that's very cheap.
There's one of its caves. There's another one. They just have huge, huge data centers. So even though we're talking about sequential access files, even though I was talking about COBOL 80 character files, these tapes that we think of as being something from the 60s are still very much with us. But of course, to get to them, because it's a tape, you have to work your way through. And it's sequential access. And that's fine if you're doing a backup. If you're doing a backup of your whole disk, that's fine. Store the whole disk on a tape, away you go. Because the time you use that is if something happens to your disk, at which point you read it all back again. Sequentially, you don't particularly care about getting to a particular piece of data quickly. Sometimes, of course, you do. Sometimes it's okay just to have sequential access. Read the next record, read the next record. More often, it's going to be direct access. Get me chapter 12. Get me chapter 3. Get me chapter 3 page lecture recording. So we also have files where we can do direct access, but that suggests that the file is organized because we have to know what we're pointing to. So it's organized in some way, whether that's a traditional database having records on people, or whether it's that OneNote notebook with different sections and different pages, or whatever it happens to be, we can jump straight to it. And of course, if we can jump straight to it, we could do that we could do sequential access as well. Okay, so if we can jump to a record, the question then becomes, well, which record do we want? If we are jumping to a record in a database, we're probably not saying jump to record 67. We're probably saying jump to record Flintstone, F. So that suggests that we need some extra information. Something that's stored along with the file that says what's in the file, if you like. And that's called an index. One of the nice things, of course, about an index, and anyone who's ever looked at one in a book will understand this, the index in a book is a few pages. So you might have a 5-page index to a 300-page book. And we have the same sort of thing in a computer file. If we have an index into our data file, we could also store that index not on disk, but actually in memory. So if we're looking for a file, we can look for it that much faster to know where it's going to be. So we end up with something like this. We have an index file that points to a particular part of a file on disk. And as I said before about Oracle and other operating systems, that's quite often built in to how the system works. IBM, who are the masters of storing massive amounts of data, have something called Isam. indexed sequential access method. So the records are all stored in a sequential access medium, like tape, but they're indexed. So you know where to go in the disk. And that's why when you saw those tapes moving around, it was moving to the correct piece of data. So you get the cheap storage of the file on disk and a tape with a relatively quick access to it as you need it. And of course, if you're doing the sorts of jobs that they are doing, and remember, we've been talking about this all along, how you set up your operating system will be different depending on the kind of work that goes through. If you know the kind of job that you're going to be doing is, for example, running through a whole bunch of transactions for one day, all of Tesco's credit card transactions for that day, you can use this method to say, okay, my next one is at position 10. And while you're processing that, you know that you're going to be doing the next one. You can say, oh, the next one's at position 27. So while I'm processing, go and get me the one at 27. So you can read ahead as well. So you can start to put in more tricks to speed up, but still keep costs down. All sorts of operating systems use this. Oracle, ZOS, VMS, piles of them. Coming back a wee bit more to more everyday operating systems, quite often one of the things that we want to do is organize our files. Before I go into that, I'm not seeing any questions. I'm not sure that I mentioned. I usually do every week. Put up your hand, put something in the chat, or just unmute if there's anything you want to ask. I do see a couple of hands, but I think they're up from earlier when I asked for a virtual show of hands for something. And the fact that they're going down just now would support that assumption. Adam, you've got your hand up. Is that just a hangover? Adam's going to sleep. Okay, taking it back into a more everyday ones, one of the things we often want to do is organize our files. And we put them into directories. I think Windows calls them folders. A directory is just a pointer to a bunch of files. So it points to the files that we have in our directory, a way of storing things. Because those files, of course, will be stored somewhere on a disk, and they won't necessarily be contiguous. They won't be one against the other. And we don't want to set them up that way because we don't want it that we have to map out an area of the disk that we're going to store for movies, and another for music, and another for documents, and another for whatever. We don't want to say, oh, we want to take up this amount of space on disk. What we want to do is say, these are all going to be grouped under music. And then when you create a file, say, yeah, I know that that's at position 10,000 and my other file's at position 15,000, but they're both logically under music. That brings up a whole other question, which is, how do we point to a file on a storage medium from where we are? So let's think about where we are storing things. So we'll talk about disks, but actually these principles apply to anything. And the first thing we can do is we can take a storage medium, a disk, and we can divide it up. And that's done quite often. Almost all of you who have bought a machine lately, a desktop, a laptop, whatever it will be, will have noticed an extra partition on your disk. And it's quite often called a restore partition or something like that. Basically, it's another partition on the disk where if something goes wrong with your machine, you can get your computer back to its initial state using the data that's stored on the second partition. So what we can do is take one physical storage medium, one physical disk, and pretend that it's more than one. That's called partitioning. So we split up the disk into multiple partitions and we treat them separately. Even if you don't have that, you can set it up so that, for example, all your programs are stored on one partition, say your C drive, and all your data is stored on a second partition, which we'll call the D drive. Why bother? Because if you're backing up, you probably don't need to back up the C drive. If you installed a program, you've probably got a disk or an online installation. But your data does need to be backed up. So if you're backing up, you can just back up your data drive and ignore your programs drive. So we can do things like that. We can start to think about what our data is and where we want it to be stored. We also need to think about how we're going to store it. And anybody who's set up a machine from scratch, so if, for example, you followed the tutorial on installing Linux, and I hope you did, because one of the things that we'll have asked you to do is format your disk. In other words, setting up the disk so that we don't just have a random block, but it's actually set up so that we can go to a specific portion of the disk, which we can then relate to a specific file. So thread.txt is at position 15,000. So we've got disks we can split up into partitions. We can give them a name. So if we have a particular file system, that's called a volume. And I'll do my usual reminder that if anything's on blue on the slides, probably worth remembering. And one of the things that we have in that volume is where things are. So we have a record of where things are. So one of the things that the file system has to do is remember where files are and be able to go to them. So we can start ending up with things like this. On the left, we have a single disk that's split up into two partitions, each of which has a directory pointing to where the files are. And the second one has a third partition called C, but actually it's made up of more than one disk. So here we're saying, yeah, I know that we've got more than one physical disk, but as far as we're concerned, it's just one big chunk of data. So for example, you guys have a OneDrive. And on that OneDrive that UWS give you, you get to store up to 1 terabyte of data. Now, I don't want to burst your bubble, but you do not have a dedicated 1 terabyte drive sitting in a box somewhere. What you have is an allocation of 1 terabyte. And when you think about it, that's much, much better. If you have 1,000 people all with an allocation of 1 terabyte, how much space do you need to allocate to those people? Well, here's a hint. The answer isn't 1,000 terabytes. Because people use their data in different ways. You guys are computing people. You will store lots of data. You'll store lots of files, lots of programs, lots of whatever you're up to. And my apologies if the example I'm going to use is completely wrong, but I'm just going to choose another discipline. I'm suspecting that if you take social science, for example, you don't store as many files on your OneDrive as people in computing do. So your average might be 100 gig, and somebody in social sciences might be 20 gig. So you're using 1/10 of your allocation. People in social sciences are using 1/50. So you can say to people, yeah, you've got this space, but you don't actually need that amount of physical space to have. What you're saying is, here's a notional amount of space. But what you're doing is also allowing yourself to add once people do start to store that data. So if you're doing this in real life, you will set it up and you'll say to everybody, right, you've got 100 gig here. And of course, when you're just setting it up, nobody in your organization is storing 100 gig of files. But as time goes on, they do. Number of files they store, the space they take increases. So you might have to store extra data. You don't want to suddenly say, oh, by the way, you're now going to a different disk. You want to do that all in the background. So what you want the operating system to do is say, okay, so you've now got this extra physical disk and you want it applied to this partition, no problem. We'll just kid on it's one big logical device. And no one else needs to know any different. So we can do all of these things, assuming that the operating system supports them. And also assuming that the file system supports them. And again, if you did the tutorial on Linux, it would actually have asked you what type of file system you wanted to use. I think from memory, and somebody can correct me if I'm wrong, the default is FS2 for Linux. But there's a whole pile of file systems that we can use for different reasons. Your USB drive probably is a FAT32 drive. FAT stands for File Allocation Table. So in essence, what you've got is a directory and a bunch of files. Instead of a directory, FAT calls it a table, and it says your file has a table. Your file is referenced in this table, so I know where it is on your drive. FAT is fine, but what you have to do is allocate a table to begin with. You have to say, okay, this first bit of the drive is for my file allocation table. And then there's one of these compromises you have to make. If you make a really big table, so you can have lots and lots of files and point to different parts of the disk, then you're taking up a huge amount of the disk to begin with. If you have a small file table, you can't point to as many files. And it's not just about the files themselves, it's also about the size. So if we have a file system come on, computer, you can do it. If we have a file system that's impressively slow, and we have a table, a file allocation table, that has a finite amount of entries. So if we say there are 32 entries in the table, that means that we get to point to 32 discrete parts of the disk. Okay, so each of those entries points to one of these sections on the disk. And that's fine if your disk is quite small, which is why things like USB drives still use it. But what if you've got a big disk? Because in essence, what you're saying is if your file allocation table has a 32 entries and you have a 512 K USB, each of these sections is 512 divided by 32. So you have 8K sections. So every file is allocated 8K, whether it's a huge Word document or a small text file. You might say, okay, well, let's have more than 32 entries. And that's fine, you could have more than 32 entries. But that means that your file allocation table gets bigger. And a bigger file allocation table means that you lose storage space. So there's a trade-off for each of these things. As your file table gets bigger, it takes more space. The amount that you allocate gets lower. So you waste less space, but you need to store a bigger table. In the jargon, fat doesn't scale. So a fat file allocation table method doesn't scale to larger sizes of storage, which is why it's largely been superseded. It was used in the early days of DOS and even in the early days of Windows. But there are different file systems. Windows now uses NTFS. As I say, Linux uses FS2. Somebody can remind me what Mac uses. But weirdly, almost all of them use FAT for their USB drives. And most consumer operating systems can read FAT because it's easy to implement, it's quick, and for small devices, these scaling issues don't come into use. So it means that you can have a USB drive that you can use anywhere. That also suggests that we can have multiple file systems available. So it's not just about deciding, okay, well, let's have one disk. These partitions here could actually be running different file systems depending on the type of data that you wanted to store. And there's some examples on there. As ever, one solution doesn't fit everyone. Okay, so we have these directories that point to files, APFS for Mac, thanks Jen. And we have operations that we perform in files, and we similarly have operations that we can perform in a directory. And again, these won't be a huge surprise to anyone. What we need to do, though, is that we can find things. We want to be able to find things quickly. We want to be able to have a naming system that doesn't clash with each other. So if two people in a multi-user system call their file thread.txt, they can't clash. And we also probably want to have some sort of grouping that says these are music, these are video, these are whatever. A single level directory doesn't really do that. If we just have one huge directory where all the files are in it, then we can only have one file for each name that we use. And we also have no way of grouping them to tell us what type of file that they are. So we can start moving into multi-level directories. So there's a two-level directory where you might say, okay, well, we're at the top level for this multi-user system. We'll have a different directory for each user. So user one can have a file called A. and user 2 can also have a file called A, and in fact so can user 3 and so can user 4, but these are different files. But we still don't have the grouping, so each user still has in essence, a single level directory. So the next logical step is to have this kind of tree structure. So we can start to point to lower and lower levels in a directory structure. This is actually quite efficient. Because we have a tree structure, because we have things grouped, instead of going through every file, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 17, 19, 22, 23, 24, 25. So to find the file first, we would have to go through 25 files. But if we know that it's not just file first, it's file spell, mail, print first. Instead of 25, we suddenly have 1, 2, 3, 4 links. So our search gets faster. We can also group things. We can give names to directories, programs in here, print files in here. And it allows us to uniquely access files even when they have the same name. Because we have this directory structure. It's not just first, it's spell, mail, print first. Or in the example, spell, mail, prog. So we can start to have a tree structure where we can access things either absolutely starting at the top and working our way down, or if we had got as far as spell, mail, prog, and we were in this directory, as it were, we can just say, oh, we want the list file. So we can type a list. So we can have an absolute name where we start at the beginning, or we can have a relative name talking about where we are. And all the things that we've been talking about in terms of creating files or directories and how we structure them and all the operations that we have can all work in each of these directories as well. It also means that we can quickly prune our tree. If we delete this mail directory, everything that's enclosed in it, including all these directories and all the files that are in those directories, can all get deleted. Hugely powerful and hugely dangerous. Because if somebody happens to be up here and says del star, where star is a symbol for everything, it'll just take away the whole file system. If you have enough rights, and we'll talk about that later. Really helpful, good for efficiency, good for file name, and good for access. Sometimes, though, we want to share things. Again, we've talked about this before. You might want to do a spell check in Word or a spell check in PowerPoint. You don't want a different spell check. You just want to call the spell check. So sometimes, and in this case, it's not a spell check, it's a word count, we'll call the same thing. This starts to get quite tricky because we now have two things pointing to one object. So count is pointed to from there and count's pointed to from there. So we need to be really careful when we are deleting things. When we delete this count directory, does it also delete this count object? Well, presumably not, because this count directory is also pointing to that count object. So what we really want to do is delete that without deleting this object, it's just the pointer that we change. So it starts to get really tricky, particularly if you start to get back pointers. So if we work our way through and say, for example, oops, say, for example, this also pointed to that object. We now have a whole loop. That can get quite tricky. So we need to start to have solutions for that. So we need to start thinking about how we point to things. So now we don't just point one way, we point back the way again. Back pointer. So if we delete something, we can check to see how many back pointers there are and see whether we delete the object or whether we just delete the pointer from where it was coming from. We might also have different names for them. So one might think of the spell check as spell check, and one might think of it as SC, but they're still the same thing. So we need to add in extra things to work with that, including links that point to them and resolving links. In other words, it doesn't actually point to the thing, it points to a pointer to the thing. So it starts to get quite complicated. It's called a graph. And it means that you can have pointers to things all around the file system from all different places. And Unix incorporates this. So you can make a link to a file. So you can say link to file accounts and call it A. So you now have a link in your directory called A that actually points to the accounts file, but you can treat it as if it was the accounts file. So it starts to get quite complicated. And if you have this cycle thing, if you have stuff going round and round, you have to be really careful that you can sort that. It's so tricky, in fact, that a lot of operating systems have something called garbage collection. Every so often they go around the tree and just check to make sure that all these links are pointing to the right place, that they don't have anything that's hanging out there, not pointing to anything anymore, and all that kind of stuff. So we need to actually put in all these things just to make sure that we keep things correct. And we're doing this, of course, because it's helpful for the user, but it does make more work for the operating system. The other thing that we need to do is attach a file system to the operating system. And again, you might not really think about that as being something that happens. You might just grab your USB stick and plug it in. In Windows, if that's what you're running, or Mac, if that's what you're running, we'll just go, yeah, no problem. I can see you've got a new device. I've called it USB stick. Help yourself. Files are there. What it's actually doing, of course, is mounting it. And it's mounting at a particular place. So it might say you're on, if it's a Windows machine, it might be, oh, I see you have a USB drive. It's here on drive G. On a Mac, it might say, oh, I see you've mounted a USB drive. I've mounted it as USB drive. Other operating systems allow you to put them at particular places. So you might, for example, have an operating system where your file system for your user files is one set of devices using one set of file systems. Your devices for your programs are on another physical device using a different type of file system. And your data for your main processing is in another set of hardware using yet a third type of file system. And those will all be attached at the right point. So your user files will be attached under users. And as far as anyone using the system is concerned, oh, you just go to the directory users. But actually, as far as the operating system is concerned, the directory users is actually another device connected at that point and given that alias. Excuse me a second. Thank you. So the operating system works out what it is, where it is, and how you access it. For simplistic user type, single user things like Windows, you don't get the option. And you often don't notice this happens. Oddly enough, the only time you do notice it is when you do something wrong. As you probably know, in Windows, you've got a remove this device option. If you don't do it, Windows gets upset and says, oh, you have removed your USB drive without unmounting it. And it gets upset not just because you've done that, but because there might be operations happening. You might be saving a file to that USB disk and you physically take it out before that file's saved. So you don't know what can happen. That's why you've got the remove option. And sometimes it will say it can't remove it because things are still being used. You've got a file open, you're saving things. So it's really important to make sure that file systems are mounted and unmounted properly. Another thing, as we said earlier, when we looked at that Mac file information system, was that we might want to share files. And you're used to that. I share files with you, you share files with me, but we need to decide how we're going to put that into the operating system. We need to know who owns the file. We need to know which groups they're a member of. So I own the file, I'm a member of the operating system's class. So I own it and I can change it. I'm a member of the operating system's class, so I can view it as part of that, as can you guys. So we need to start thinking about having all of these pieces of information stored with the file. Who owns it? Who has access to it? Who can change it? All that kind of thing. Thank you. Tea time. Cheers. That then becomes more complicated when you have things like removable drives, like your USB drive, or other removable drives like network drives or cloud drives. So I'm just looking at my file system at the moment. So I've got a drive C, which is, that's an SSD as it happens in this machine. I've got a drive D because this machine allows me to put a micro SD card in and use that as a drive. So that's my drive D. I've got a drive F because I've got a USB drive plugged in. I've got a drive G because I have a Google Drive using a Google file system, and that identifies itself as drive G. I have a network file system that I use for backups in my house, and that on my Windows system is identified as drive N for network because I've told it to be N, and that's how Windows works. On my Mac, it's identified as backup drive. As it happens, I don't just use it as a backup, I also use it as a file store. So as well as drive N for network backups, I've also got a drive M for music. And again, on my Mac, it's just shown as the music drive. So I've got all these attachments all pointing to different places. And I haven't even talked about the fact that my OneDrive is also there with links. And all of these different systems need to know who owns them. And it's fairly clear when it's my machine and it's the SSD. Well, it's my machine and it's my single user machine, it's mine. What about my internal network backup? Can anyone who connects to that hard drive from inside my house access that file? What about the stuff that's on my OneDrive and my Google Drive? Who can access those? So there's got to be a whole scheme set up that decides who owns it, who can access it, and all this kind of stuff. So there are actually whole protocols written, including NFS and CIFS, to allow that to happen. It allows me to mount remote systems like my OneDrive and then share them in the right way. So the file system moves beyond just being a file system to store on a physical drive. It moves to being a file system to allow you to communicate over networks. So that's called a distributed file system. And there are other subsystems that exist to ensure that that works properly. Where is it? What's its name? Who owns it? And there are lots of different naming services that allow that. So for Windows Server, for example, it's called Active Directory. Other systems use different things, like LDAP. All of which decides who can do what and when for those kinds of access. Linux, for example, identifies 3 different categories. There's whoever owns the file, the group that they belong to, and everybody else, which it calls public. And it gives 3 options, whether you can read, whether you can write, and whether you can execute for each of those 3 categories. So you'll see quite often on Unix systems, when you look at a file, it's writes, which might say something like 761. Read, write, execute, we're using binary. If it's 0, you don't have it. If it's 1, you do have it. So 111, as you well know, is 7 in binary, so the owner has all access, read, write, and execute. The group can read it and write it, but they can't execute. 4 plus 2 plus 0 is 6. And the public can access it, but not read and write. So this might be something like a game that's on your machine. You've got complete access. Your group can alter it to add in extra packs, and everybody can run it from wherever they are. Windows has a similar sort of thing. So if you ever go into the security tab, when you get a file properties, it will talk about an access control list. So there's a list of people who have access, and when you click on each of those, it tells you which type of access you have. Full, modify, read, execute, and so on. It's just the same thing, but done in a different way. So that's a file property in Windows. If you do a file list in Unix, you get something like this that gives you this read, write, execute stuff, with this extra one at the right to say whether it's a file, in which case you get a dash, or a D, which means it's a directory. So there's a whole pile of things to take into account for file systems. That's just some of them, but they're the main things. Anybody got any questions?
None from me.
Okay. All right, let me stop the recording if I can.